Hello community, so great that you are back. Today we look at, hey, can AI tell us if a certain statement is true? And then would say, AI, yes, AI for everything. No, here we have February 23, 2025. Young coders are using AI for everything. But giving a blank stare when asked, how does it actually work? So you might say, hey, AI is not about code or science. AI is about investments. It is about profit for our global investor. Silicon Valley and the US economy depend on AI. Just look at the stock market. Look at the importance of NVIDIA for the US economy and even national security, Google tells us, no? And yes, I know you're right. And I know that there are some AI models that are currently offered by startups to fact-check single tuples of data. And yes, of course, I know that AI models hallucinate, and they even hallucinate sources. But yes, I know that we have a RAG system to kind of help us here a little bit with those hallucinations. And yes, I know that AI models get the relations wrong. And you might say, but therefore we do have knowledge graph integration, no? Like graph RAG. And you might say, AI models now do deep research. So there is now the solution to your question. Can AI detect if something is wrong, incorrect, factually not what you expect, a plain and simple lie? So let's open up this video. Let's have a look at this. This deep research, hey, I did just a simple test. No, OpenAI deep research, beautiful. I go down and make a meta-analysis and say, can we use AI not only as a fact checker, but also as a general verifier of long and complex information? Is it easy to fact-check a single sentence? Of course. But what about a long and a complex text that might contain some correct data, but also other incorrect conclusions or incorrect interpretations? I think this is a problem. And then here we have deep research by OpenAI comes back and says, hey, specify if you're talking about a scientific verification, a journalistic verification, a computational verification, or a legal verification. And I take all of them. And you see, here we have now the result for deep research by OpenAI. Let's have a look at this. Let's look here at the thinking process, the activity that we have here. So this is what OpenAI was thinking. It was gathering information on AI models like transformers, knowledge graph, focusing on the logical consistency and the historical accuracy. It was searching for transformer text consistency verification, for knowledge graph fact-checking. Yeah, this is nice. For multi-agent adversarial fact-checking. So exactly what I specified in my title. Then exploring the possibility of obtaining a direct link through a paywall. No, this failed. Implemented the scroll functionality in the new client interface. Okay, whatever this means. I'm mapping out a survey on claim detection and verification, not what I asked for. I'm gathering here truthfulness metrics. Okay. Fact or fiction? Well, not really. Digging into alignment with scientific principle and fact-checking? Maybe. Search for multi-agent fact-checking AI research. So multi-agent framework, results. Yep. Logical coherence detection, a BERT-based model, not really. 2020, not really, it's 5 years old. Logical consistency, not really. Here, verification of 2018, 7 years old. Not really. Here, dataset 2021, 4 years old. So T5, my goodness, a T5, 5 years old. 2018, okay, you got it, 2018, yeah. Okay, here we go on, read more from Archive, at least Archive, great. I'm noting contradiction in the detection methods, yes. Ensuring here whatever this is, thinking using here DeepMind retro concept, well, okay. BERT-based, GPT-3 accuracy. Stone Age, okay, 2020, okay. I'm digging into the defined set and a clear list compiled. So after 8 minutes, this was the sort process. Then we do have the 24 sources. Beautiful. At least I know exactly where the information is coming from. And now I ask you, what if these are not the perfect sources? What would the result look like? Well, we have it here on this side. So we have transformer-based models for contextual verification with GPT-3. Great. With a method by 2021, 4 years old. Then GPT-3 performance, oh, this is great, maybe we skip this. T5 or BART, 5 years old, 2020, 5 years old. Cambridge 2023, hello, yes, only 2 years old. Yeah, 2020, 5 years old, a BART style encoder, 5 years old. Wikipedia, great that we have Wikipedia. 1990s, okay. 2018, okay, yeah. Consensus would be great if we would have something 2018, yes. 7 years old, BERT, stand for 2008. Wow, I'm really amazed. Yeah, GPT-3, great. Scientific fact-checking in context, CyBERT, 2020. COVID-19, no, please don't, not more about COVID-19. OpenAI GPT-3, oh, great. So 2020, 2021, 23, 21, 23, 23. Benchmarks, yes, 2022, fact-checking. So this is it. This is now the deep research. This is now the solution for everything. So if I have now a look at OpenAI deep research, and this is me, and this is the beautiful OpenAI, you know what I think? I think this was quite a failure, huh? So what to do next? Now, let's think about fact-checking. I would say, hey, fact-check this. Wolfgang Amadeus Mozart, he was a famous composer, especially here in Europe, in Austria. And you say, that's so easy, no? Fact-check this. We are talking here about the same person, but now we are talking here about the European landscape, feudalism, mercantilism, early capitalist impulses. We are talking about aristocratic patronage at this time. We are talking about the relationship of the church with Archbishop Colorado here in Salzburg. We are talking here about his public concerts. We are talking here about other problems like financial fluctuation. We are talking here about his public subscription concerts. We are talking here about the interwoven socioeconomic matrix. This is not at all easy to fact check. But you know, this is now interesting because we go from a single point fact checking to check if this is a correct statement. And think about this as a medical statement. Maybe it's a medical statement about you. Do you want it to be right or wrong? So I know what you're going to say. You say, hey, let's build a knowledge graph. So let's do this. So I take here my beloved Wolfgang Amadeus Mozart, and I start to build here a knowledge graph. Yeah, and the first 5%, and just goes on and on and on, and we can build a knowledge graph, and great. But you know what? A knowledge graph would need additional information for all these other elements, like the economic situation at the time, the political system at the time, the aristocracy at this time, the specific personality of Wolfgang. He was not maybe the most simple person. His family background, his friends, his partners. So there's so much information, so much data missing to have here a validation of this complex paragraph. So we need a spark. We need a spark of genius here to solve this, no? So what we have our LLM, we have the parametric knowledge that the LLM has been pre-trained, supervised, fine-tuned, and aligned for. Great. And then we have RAG, no? In my last video about RAG, GraphRag, LightRag, and PathRag, I showed you the latest technology to implement the RAG with external data. But you know what? This GraphRag, this is embedded here in an ocean, in a sky of information, in a universe of data. So how we handle those, how we handle the integration of GraphRag into this universe of data. Now you might say, hey, wait, GraphRag is limited, no? GraphRag is limited to my personal data, or the company documentation, or to my personal text databases or the corporate databases, because I have a specific query to my LLM, and GraphRag just has a very tiny amount of additional information. And yeah, the parametric knowledge of the LLM contains the complete garbage of the whole internet. But how do we now assess here background information about the political system, about the financial system, about the economics of his time? So what we need is here to detect the missing links. GraphRag and PathRag and any RAG system cannot detect those missing links, and we need to find those connectivity to validate the paragraph. So how we do this? It's easy. Let's make a Gedankenexperiment. Let's say we have here, if you're in the US, you know CNN or Fox Entertainment, and they bring you a story about the identical event. And they present it to you in a particular way. They give you here particular data, and let's say they present it here in a positive view. Now, another channel might look at the absolute identical event, but they have a different predisposition, no? They will not give you some data over here, but they will focus on a different data set that is maybe allocated in a different sector in our knowledge graph. And they might not even make any connection to some other sectors. So they look to implement missing links so that their knowledge graph, that their story, their complete data information is rather limited. And CNN is also rather limited. And then you go on Twitter, what used to be Twitter, and then you have an even higher simplification, maybe just a linear pattern where you say, my goodness, who are those people that post those nonsense? So how can we build an AI system that takes care about this? And I know that you know the answer, and the answer is simple. It is CNN, no, it is GNN, a graph neural network. And why? Because there the mathematical apparatus is message passing algorithms. Now let's come to the core of this new idea. What we do is we have a claim. No, this is somebody claims this. And then we have, let's take from CNN here, their reporting. So what we do, we build here from those two text passages here, we build here a knowledge graph from the claim and a knowledge graph regarding here the encoding of this relevant documentation. You see immediately that there we lose some data. But for training data, we have a label 0 or 1, depending if you think that it's true or not true. So we can train here something on this. And you might say, but hey, you showed us videos here, like here, the DeepSeek agents, and we have a knowledge graph built from the reasoning traces in the dynamic memory. And then we just say, hey, here's my knowledge graph, and this will help you to solve my specific query. And yes, you're absolutely right. Or you might say, hey, in this video, we looked exactly here at sync-on graph. So AI reasoning with a knowledge graph and where the agent works on the knowledge graph itself. So why can we not use these things? Now, our next challenge, if we go now the next step in the complexity, is to integrate a broader context. Economics, financial perspectives, personality traits, social norms, everything, and to detect the missing links that explain or uncover new data for new investments. So you see, it is not anymore that we are limited to the knowledge of a graph, but now we integrate the graph in its complex environments. Economics, finance, personality, medical, physical, whatever you want. And this happens here with a graph neural network. Now, you know, if you're a subscriber, hey, look at this. 3 years ago, I started here with videos here on knowledge graph embeddings here. I have a complete list here of 29 videos. So you'll find everything from message passing here in the code of a deep graph library, or if we have here unlocking the potential of message passing, exploring here GraphCHECK, and other graph machine learning representation in a computational graph. Here we have the link prediction in PyG or in DGL, the deep graph library. Here we have a little bit of mathematics from 2022 about the Weisfeiler-Lehmann test. Here we have a neural Belmont for GNN interpretation. And for those who like a little bit of mathematics, the importance of Lie group with the deep learning and graph neural network. So everything is there for you. If you're not familiar, never mind. It's an easy explanation. Message passing, and we have 3 main modes of operandi in message passing, allows here each node to aggregate information from its neighbors, effectively building here a contextual understanding of its role within this particular graph and its relationship to the other entities of the graph. So GNN do not just compare structure of graph, but they process here the structure to learn to extract here the meaningful pattern and the meaningful relationships from this graph. And this now allows us here more nuanced reasoning beyond simple a graph matching exercise between knowledge graphs. So we have here a much more flexible and much more learned form of comparison than just comparing here the raw graph knowledge structures. So let's come here to the facts. We have a beautiful new study. This is from University of Tokyo, Texas A&M University, University of Cambridge, Duke Medical School, Aarhus University, and Yale University, February 23, 2025, and it is about GraphCHECK, breaking here the long-term text barriers with extracted knowledge graph-powered fact-checking. And you might say, hello, this is exactly what it is. So what is the key insight? Structured knowledge helps us here to have a fact-checking or a graph-checking here especially when we have long and complex texts in front of us. So what we do, the new element here is to use a graph neural network to process the knowledge graphs. Because the graph neural networks generates graph embeddings, and they are then used here as a soft prompt, and I will explain in a minute what is a soft prompt, to guide here the LLM's fact-checking process. So this means that we will use, in this particular case, our graph neural networks. They can act as effective knowledge integrators for LLMs in more complex tasks and fact-checking tasks. Now, the simplest form is somebody claims something on the internet, we have a little documentation, and we just ask, I don't know, Sonnet 3.7, hey, is this true or not? Much better is we do here the same thing, but now we have here the claim might be a complex claim, multiple sentences. So maybe we divide it up in single sentences, and then if it's a long sentence, we divide it up in parts where words go together. We have atomic claims, and from the documentation from RAG, we have all the chunking that is happening. And then we go from pairwise, checking, 100 of items. So we have multiple LLMs calls, but we are fine-grained. But unfortunately, if this is a huge documentation, this is absolutely inefficient because it takes us a real long time. And now the idea of the authors of this main study of today is simple. We have here, again, our claim by somebody. We have our documentation here. We simply provide also this text information to the LLM, but we also build knowledge graph. Those knowledge graph we then transfer with a graph neural network, and the graph neural network does a specific embedding for us, and those embeddings are then in a specific mathematical space projected into a coherent vector space that the LLM can understand. So what we do, we have the text information plus the additional graph information. And everything is now in a mathematical vector space with our vector embeddings. So we provide simply, if you think here in the first case, we only had the text information, and now we provide here the knowledge from the knowledge graph and the GNN mathematics for the embedding. This is all there is, as simple as this can be. Here I give you an example from this publication. There's the claim, simple idea, and then here the document from some official sources or whatever you go. So we build here for both ideas here a knowledge graph. You see, easy. Now you could say theoretically, hey, just let's compare the knowledge graph in itself. Let's see if we have similar nodes, similar edges, and this is it. Yeah, but what if not? What if there are links missing in one of the graph? What if there is an additional background information that we need to verify or falsify this? So here, if you want, the graph neural network idea comes in. So let's have a look now at the complete structure here, how we do this. So again, we have here a document text. This is our official text. And then somebody on the internet claims something. Yeah? Paracetamol is safe in any amount, and ibuprofen can cause stomach problems. So what we do, as I showed you, we generate our triplets. We just ask, I don't know, ChatGPT, whatever, to generate triplets. And then from those triplets, we build a knowledge graph. We build a knowledge graph for the main document, medical database or whatever you have, and then a knowledge graph that we call a claim knowledge graph from this person here. And this is a rather easy one. And you immediately see, if we have paracetamol is safe in any amount, there's no link because the only link here is safe to any amount is not supported here by the document knowledge graph. You might say, beautiful. But now comes the interesting part. We have here a knowledge graph and another knowledge graph, and somehow we want to transfer those knowledge graphs into a vector representation that the main LLM with self-attention layers, a classical transformer architecture, can understand. So what we do? We provide here, of course, the document text and the claim text here with a simple embedder. We provide here the text tokens to the LLM. Beautiful, no problem at all. But now we have a different mathematical representation in a different mathematical space from the knowledge graph. So we have also to encode this and project this embedding structure into a new vector space that is compatible with the vector space of the LLM. And this LLM here is our verifier LLM. So you see, there are a lot of transformation happening. let's look at this. So this point here is really important. So again, to align here the graph embeddings with the LLM textual embeddings here, a projector is used. And this projector module maps here simply the document graph embeddings and the claim graph embeddings, those are those two here, coming down into a projected graph embedding that is compatible, coherent with the LLM embedding space. So we just transform representation in some vector spaces and some mathematical spaces to other mathematical spaces. There's nothing special about it, but there is a problem, and I'll tell you in a minute. But of course, this encoder we have to train a little bit, that it really does what we want to do it. So we have a graph pre-training with some external data, and I already showed you here some external data at the beginning of this video. And then, finally, as you see, we have here the projected graph embeddings coming up here, along with the text embeddings. Those are text embeddings. They are now concatenated and fed into the self-attention layers of our verifier LLM. And then the LLM performs fact-checking and outputs now a label, true or false. It sounds so easy, but you know the devil is in the detail. Because they use now soft prompts. And I was not really familiar with soft prompts, but let's have a look at this. So they're often learned or optimized through the training. And in GraphCHECK, like ours here in the graph neural network and the projector model, they are really trained to generate graph embeddings that are most helpful for the LLM in making here some fact-checking decision. So you have to learn this particular representation, and this is key to their effectiveness. So note, those are not just arbitrary vectors that we generate, but they are tuned here to guide the LLMs toward a better performance. The magic happens here in the embedding space. So by concatenating now the projected graph embeddings with the text embeddings of the document and of the claim, we are essentially augmenting here the input representation that the verifier LLM will process. And it is exactly as I showed you already. This combined representation of the text embedding that is coming down here and the graph embedding that is coming down on the other side, they both go now into the LLM self-attention mechanism. The graph embedding, even it's not human readable text, influences now the LLM, how the LLM attends to different part of the textual inputs. This is the main thing to understand. While it's true that within the graph neural network, each node has its own vector representation, but in this particular GraphCHECK implementation by the authors that we talk about today, they used here a specific readout function. And they now have a summation. So they now say, hey, let's sum over everything. So we aggregate all the specific node vector representation in a specific mathematical space into a single global graph embedding vector. So the whole complex graph is now a single vector in a high-dimensional mathematical space. Between you and me, this is a very easy, very fast calculation, but we lose a lot of detailed information. And this single global graph embedding vector now is what really represents the entire graph to the verifier LLM, and this acts now as the soft prompt because it is a vector representation. And this is exactly what is also happening in the first layer of a transformer architecture. So, short summary, GraphCHECK, this methodology simply concatenates the text embedding and the projected graph embedding and create here a combined input vector. And from the LLM perspective of a verifier, the one in the bottom here, it is just receiving here as a vector, as an input. Now this vector has concatenated those embeddings, but the LLM doesn't care because albeit a vector that now contains information from both the text and the knowledge graph. So we build now a vector from the text and the knowledge graph and if you want, the dense environment of all the nodes, of all the text elements. We have here the node and the edges constructed. And we have now, if you want, all the surrounding information from the knowledge graph integrated in this particular vector. But remember, this graph vector is a summation over all node vectors, which is it's a strong estimation. Okay, next one. Please be careful because the authors doing here all these studies tell us here for these long form documents, like this huge paragraph I showed you about Wolfgang Amadeus Mozart, the completeness of the knowledge graph is critical. So all the textual information, all the semantic encoding must be converted into the triplet structure for the knowledge graph construction. Now they found that those triplets extracted here by an 8B model were not so great. Those 8B model lacked here crucial details. The time was not there, the reasoning was not there. And they give us here an example. Here we have the document, this is the official document, and somebody claims something on the internet. And then you have here the Claude 3.5 Sonnet, 4 Omni, DeepSeek version 3, and the 8B. And you see those bigger models here, they have no problem here to convert this here to a knowledge graph representation into triplets, but Llama 8B misses out on some facts. And therefore, Llama 8B is the only model that comes to the wrong conclusion. The other three gets it right. So we have to have a LLM model that is really able and really checked that it is able to extract here all relevant information for a knowledge graph representation. Now let's look here at the final result aggregated over, I don't know, 1, 2, 3, 6 benchmarks. The GraphCHECK Llama 3.3 70B. So 70B is a rather huge model. If we take overall is 71. The GraphCHECK with, if you want, Q172B is 70.7, so close to 71. But, and this is beautiful that the authors give us here also the performance data, if we only do GraphCHECK for my last video with a GPT-4 Omni, so unfortunately the 4 Omni is, I suppose, bigger than a 70B here, but the GraphCHECK has a performance of 70.6. So those are all really damn close. So if I just see this performance data, I would say, should I really go for a GraphCHECK methodology when I see that in this particular case that was tested, a GraphCHECK almost gives me the same performance? Okay, ChatGPT is a more performant LLM in itself. So yeah, it's not really clear. But the authors give us here a detailed performance data, and this is now beautiful. So we have here a general domain test field and a medical domain test field. And let's go with the medical domain, because it's really important. If in medicine you do something wrong or the AI comes to a wrong conclusion, this can have some massive effects. So they have here their different tests and the different benchmark. And as you can see, GPT-4 Omni from OpenAI, the O1, the 3.5 Sonnet, the DeepSeek version 3, the small scale models down to the QN 2.572B and the Llama 3.3 70B. That's some special models, and then again here in the last line we have those two GraphCHECK implementation on a 70B Llama and a Q172B. Now interestingly, so that you see that the last two lines are covered in color, they went with a nice, I call it a trick. So as you can see, they did not just indicate here the best model in color, but they did the best model, the second best model, and the third best model. Otherwise, here in public health, we would not have here a color for the third best model, because the best models are simply the original Llama 70B and Q1 70B. So you see, okay, so yeah, you get an optical impression that this is really outperforming everything else. But please, if you look closely, you see, okay, there are nuances. And yeah, but you know what? Looking at this GraphCHECK methodology, I think it's a beautiful model. Because if you watched my videos about graph neural network and you understood what we did 2 years ago from the mathematical framework, it is rather easy to build now on this idea. And we can now go and not do a summation over all vectors here in the graph, but we can be much more detailed, much more specific. So either we go for thematic clustering or we go for a node-specific evaluation methodology that the code I already showed you in my videos 2 years ago. So you see, this is beautiful, this modularity we have. 2 years later, this idea of a GNN pops up again, and we can suddenly use it here for AI, the latest in AI. I think it was so beautiful to read this study. I got so many new ideas, and I don't regret that I made all these videos 2-3 years ago, because now it is so easy to implement their ideas. And if you understood at the time what is happening, why we're doing here these graph embeddings, and what are the benefits compared to other methodologies, now it's really simple to build on this particular study here on graph fact checking here. and go the next step. So if you subscribe, maybe in one of my next video, we will do this.